Hello everybody, my name is Emin Skiljan. Today we'll be going over crystal structures. So what are crystal structures? The crystal structure of an element directly affects physical properties of materials including hardness, density, and conductivity. So the material properties, the crystal structure directly affects the physical properties of materials including hardness, density, thermal and electrical conductivity, and optical properties. For example, the difference between diamond and graphite is due to their distinct crystal structures, even though both are made of carbon. In fields like catalysts, the arrangement of atoms in a crystal structure can influence reaction rates and pathways. Engineering and design, understanding crystal structures is essential in material science for designing new materials with specific properties, such as high-strength alloys or semiconductors. So, we define elements of crystal structures through their unit cell, crystallic systems, crystal lattice, and coordination number. The unit cell is the smallest repeating unit containing full symmetry of a certain crystal structure. Crystals have 7 crystallic systems, all based on the geometry of their cells. Crystal lattice is used to describe a repeating 3D pattern of atoms in a crystal, and the coordination number refers to the amount of closest neighbor atoms within the structures, also giving information on how tightly packed the structure is. So the types of crystal structures, we have SC, BCC, FCC, and HCP. Simple cubic, also known as SC, have atoms located only in the corners of the cube. It leads to low density. BCC have one atom in the center of the unit cell in addition to the atoms in the corners. FCC have atoms located in the corners and in the center of each face of the cube. HCP have their atoms packed in hexagonal layers, achieving high density and packaging. So, going over some of the specific materials we have aluminum, which is FCC, and the relating information is posted there. So that is standard for FCC based structures. We have magnesium, which is horizontally closed packed. These are much more efficient in their packing density. Then we have boron, which is a semiconductor. There's a beta rhombohedral structure that is complex. It has 12 atom icosahedra. The alpha rhombohedral boron structure is less stable than the beta form, but can exist at higher temperatures or under certain conditions. This form is a little bit more difficult to achieve and is more unstable. Nitrogen has a form that takes up alpha nitrogen. This phase forms at low temperatures and standard pressure, has an HCP structure. Another version of nitrogen that is also difficult to attain has very low density, so it doesn't naturally occur like that, and it undergoes a variety of solid state changes.
The coordination number of a metal is the number of atoms, ions, or molecules that are directly bonded to the central metal atom in a complex or crystal structure. The way we find the coordination number is by looking at the structure of the crystal, determining the type of structure it is, and counting the nearby neighbors. This is known as the coordination number. So for example, in an aluminum crystal structure diagram, we can determine, or it is just known, that aluminum is a FCC, so it has 12 close neighbors, therefore the coordination number is 12. And for magnesium, it's a HCP with also 12 close neighbors, so the coordination number is 12 as well. So now the atomic packing factor is a measure of how efficiently atoms are packed in the crystal structure. So the way we find the APF is taking the volume of atoms in the unit cell and dividing it by the volume of the unit cell. So for aluminum, as determined earlier, it was an FCC structure, so therefore N is equal to 4. And then so we just plug in 4 for an N in this equation, and that's the top half of the equation. The volume of the cell is A cubed. When you divide volume of atoms by a volume of cell, there are two unknowns, A and R. But we can have a relationship between R and A. A is equal to 2 radical 2R. So plug in A for 2 radical 2R. The R's will cancel out, leaving you with pi over 3 radical 2. which is approximately 0.74. Looking at magnesium, it is a HCP structure, as determined earlier, so N equals 6. This time the volume of the unit cell is given by this formula. A equals 2R is a relationship. C equals 1.633A is another relationship, where C is the height. In dividing and canceling out, you're left with APF equals 8 pi over 19.596, which gets you 0.74. Theoretical density is the density calculated from the atomic mass, crystal structure, and parameters of the material. So this is the formula we use. This is called rho. Rho equals N times A over volume of unit cell times Na, or Avogadro's number. A is the atomic mass, N is number of atoms, rho is density, and V is volume of the unit cell. So looking at examples again, aluminum is FCC, therefore N equals 4. Na is a constant, 6.022 times 10 to the 23rd. The atomic mass of aluminum is 26.98 grams per mole, found in a table or a periodic elements chart. And the volume of a unit cell is A cubed. A equals 4.05 times 10 to the negative 8th. So plug in all your values and we get that density is 2.7 grams per centimeters cubed. Finally, looking at magnesium. Magnesium is a HCP, N equals 6. The atomic mass is 24.305. The volume of the unit cell was given earlier. These are the constant values for A and C. Plug in values for A and C into the volume equation, and the volume is 1.58 times 10 to the negative 22nd. Now we have all of our variables, and plugging this in gets the density of 1.73 grams per centimeters cubed.
The crystalline plane family of 111 consists of the plane 1, 1, 1, and any plane that is equivalent to that. We can see those labeled here. A good way to find all the planes in this family is to plot each plane from a different edge on the cube. If we plot it from here, we would get 1, 1, 1 with the z as the negative. With this one, we get 1, 1, 1 with the x as the only one that's positive, and so on and so forth. This is all the planes in the crystalline family of 1, 1, 1. This is the direction family of 1, 2, 0. Now we're going to find the linear density of aluminum. Now aluminum is a face-centered cubic lattice structure. And we're going to take the linear density of it at the point, at the line 1, 1, 1. Now if we look at the plane 1, 1, 1, we can pick any of these lines and use it for our linear density. The formula for linear density is number of atoms over length. So we're going to take the line, and I drew it down here to show it, and it has 3 atoms on it. The 2 atoms on the edges technically only count as half. Now to find the length of it, because all of these atoms are touching, we have half of an atom, so that's the radius of the atomic radii of it. We have one full atom, so that's 2r, and then another half atom, which gives us a length of 4 times r. And the number of atoms in this are 1 full atom and 2 half atoms, which gives us 2 atoms. So plugging those into the linear density equation with the atomic radii of aluminum being 0.143 nanometers, it gives us a linear density of 3.497 atoms per nanometer. Next we have planar density. We're going to use the same plane of 1, 1, 1. And the planar density has a similar formula with number of atoms, but this time it's over the area of that plane. find the number of atoms, here we see that each of the ones on the faces contribute half of their atom to this area. So we're going to do 3 atoms times 1/2, and for each one on the edge of the triangle, they contribute 1/6 of their atoms. So we're going to also do 3 times 1/6, which gives us 2 atoms. And then the area for the triangle, for this triangle, is 4 square root of 3 r squared, which gives us an area of 0.1417 nanometers squared. Plugging that into the planar density formula, we get 14.117 atoms per nanometer squared. Here are the linear and planar densities of our other metal and the 2 semiconductors. Magnesium has a hexagonal closed pack structure, and we took the linear density at the line 1111 and the planar density at the plane 0001. And boron has a rhombohedral crystalline structure. We took its linear density at 100 and a planar density at 001. Silicon, also like aluminum, has an FCC structure, and we took the linear density and planar densities from the same as aluminum.